Hello everybody and welcome to another day of CS219, day 19, getting closer and closer to the end of the class. Today we're going to be talking about instruction sets, chapters 13 and 14. And so chapter 13 is going to deal with the characteristics and functions, and then 14 is going to be addressing modes and formats. So since it's about instructions, how about we start with how you represent an instruction in your computer? And so in machine code, each instruction has a unique bit pattern. And this you should know already, if not at least from the IAS computer, but if not from assembly class. And so you divide this bit pattern into fields that are predefined typically. And so here I have an example of a couple of the very common ones. So the first one here, we are dividing we're dividing it into three parts. We have an opcode right here, and then we have an operand reference and another operand reference. So this would be basically like a binary operator, because you are referring to two locations in memory, and then you're doing an operation more than likely in between them. Now, what kind of things could you do there? Well, it could be something arithmetic related. It could also be something where one of the operands is actually where you're getting some information, and then maybe the resulting operand is, or the second operand is actually where you're putting the result. Or potentially it could be something like a next instruction as well. So really you're not limited to one specific operand type. Also, other kinds of distribution of the bits is going to be something like like the one with the IAS, where you have a unary operation, basically. It's operator, like the opcode here, and then it only has one operand, right? So the other one is binary and this one is unary. So this is like your load and store, or more of like your MIPS kind of stuff, the simpler instructions per se. And now, depending on the computer's size of the registers or width of the memory, you have to distribute the number of bits to each of these categories. So in that example above, just to kind of go out of, to be different, here we have 16-bit basically memory width. And so ultimately, I decide, okay, I'm gonna do 4 bits here, 6 bits here, and 6 bits there, but nobody's stopping me from doing a different organization. At the end of the day, it's up to the person that's going to be basically interpreting or creating how these instructions are interpreted by the computer to separate these things. In the example with the IAS, we said that the first byte is the opcode, and then the next 3 bytes are the operand reference. But I could have just as easily said that I wanted the opcode to only be 4 bits, and then to have the operand, instead of being 24, to be 28. That could have worked as well, because we probably don't even have that many opcodes anyways. So again, this is something that is variable, and typically it's designed to be as flexible as possible, but still to be to be organized, because at the end of the day, when you're trying to write your assembly code, you want to make sure that you're able to access, for example, all addresses in memory, right? So if you only have 6 bits for the operand for the addresses, and you have in memory addresses that are bigger than that, and you have an array that's potentially bigger than that, then you're not going to really be able to access it at all. And so that's important as well to consider. And so these, of course, are all stored in binary, but sometimes it's easier to represent them in hexadecimal as well. So for example, let's just say here that we have let's say we're storing an integer, okay? And this integer in binary is just, I'm going to just pick random numbers here. So let's say that I am picking 0, 0, 1, 0, 1, 0, 1, 1, 1, 1. How many do you have? 2, 4. Well, I went too fast and now I lost track of how many I have here. So I'll split them up like this for reasons that'll be obvious in just a second. And then maybe that, okay? So now I just gotta basically double this. So maybe squish this back together. So here I have so far 16 bits. So basically I just have to double this. As you can see, this actually is pretty long thing to keep in here, right? Pretty hard to keep track of this. And so because of that, one of the ways that you represent this information, as we talked about, could be with hexadecimal. So that's probably why I have this here, because it's going to make my life easier. So how about we split this into hex so that it's easier and smaller. So let me just split it into 4s so that I can see it easier, like that. And now let's go ahead and convert it into hex. So this is a 2. This one is a B. This one here is a C. This one is a 6. And then, of course, if I happen to make a mistake here, I'm trying to go slow to not make it. It's okay. Just, it doesn't really matter. You get the point. This one is a B. This one's a C. I guess I was not that creative at all because I didn't really get that many variations of digits. But anyways, there we go. So now we can go ahead and represent this here as 2B, C6, 2B, C6. Okay? And so this is the same thing as putting that in binary, but this is a lot shorter to write, and that's why when we're printing out addresses in the machine, they typically put a 0x in front, and that represents basically a hex address, right? And so, how does this actually get stored in memory? Okay, well, there's two sort of ways that it could get stored. Now, of course, if your memory can fit 4 bytes into one line, then you can just basically copy paste it into memory, right? So, if I could go ahead and fit all this into like one row of memory, then I can just, basically copy paste it. So like, bam, something like that. However, that's not always the case. Your memory might be smaller than 32 bits. Maybe your memory is actually 8 bits, so only 1 byte wide. Okay, and if that is the case, then there's really 2 ways that you can actually store the information. One of the ways that you kind of would think it's the most obvious way, I guess, would be, well, this is basically the equivalent of one byte, and then there's 4 bytes here. And if this is each 1 byte, then why don't we go ahead and just kind of put them in the same order? So we can go ahead and basically just put the 2B here, and then the C6, the 2B, and then the C6 here. Okay? I can't believe oh, well, that makes sense because then I copy and pasted it twice. Yeah. Let's change that because I want it to be different, because when you're looking at this later on, if you're trying to review, you might actually get confused. So let me go ahead and change this to use something else. So maybe right here we can change this. Let's change that one to be a 1 1 1 1. So that's an F now, and then maybe let's change this one to be a 7. Just so they're different. Otherwise, it looks like a mirror, and the reason why will be obvious in a minute here. Okay. So there we go. Now they're different. So that's much better. I feel better about that myself. Okay. Let me re-highlight that. And here we can just use a different color for this one. So maybe we'll do that like that, and then we're saying that would go here. C6, and then the next address. And of course, this doesn't have to be address 0. This could be like address, I don't know, 4 or 5 in hex, and what I'm saying is that the next address after that, which would be +1 essentially, would be address maybe 4 6 and so on. That's where you would store the C6, and then 0x47 we would store the FB in there. So here, let's pick another color for that one. Maybe we can pick a blue. Oh, that's the pen. There we go. We're going full Bob Ross here. And then finally, oh, blue, and it's FB, like Facebook. Interesting. That's like some subliminal message probably. So there we go. Okay, so that's one way to store it, right? And that might be the way that you might intuitively think of like storing information in the case that it was only 1 byte width, right? Because that's kind of how you would do it if it was like a little array per se, C++ style, right? However, let me propose to you another way of storing it. The other way is to put it sort of backwards. So go ahead and put C7 here, and then put FB here, and that one would be that color, and then we got our C6. That's not the right color. What's the right color? I think it's maybe this one. Nope. Maybe this one. Yeah, I think that's it. And then finally we got the red. Not that it really matters, but you know, it looks pretty. Right? So that could be another way of storing it, right? And that's okay as long as you know that you put it backwards. Because then if you're trying to access things, you know, you can you just have to remember that you have to start from the bottom up if it's because it's stored backwards. And it turns out that this isn't something that you might think it's ridiculous, because it's actually used pretty often, and there's actually a name for this, and those are called big endian and little endian. There, look at that reveal right there. That was sleek. And so it actually turns out that certain systems will store addresses like this with big endian, which is like the way that you would think, and other ways of storing it like little endian. So who stores it like what? Well, it turns out that the majority of the popular architectures like x86 and AMD 64 and x86 64 and all of those, they all actually use, surprise, surprise, they actually use the little endian method. Yeah, so they store things kind of backwards, and you don't really see that, and there's actually no easy way of seeing that as a when you're programming in your computer, because this is all done internally, and it's hardwired internally to be able to split things like this in this sort of backwardish manner. And you know, if you want to ask, okay, who uses big endian, it turns out that some old computers like PowerPC, Alpha, Spark v9, MIPS uses big endian. Or sorry, no, actually, no. Apologies. MIPS and ARM actually use what is known as bi-endianness, which means that they can go either or. So ARM, actually, you can choose which of the organizations you want to do. And similarly with PowerPC and Spark v9, actually. And so you might be asking yourself, which one is better? You know, like, oh, by the way, I guess I never mentioned them. So the ones that use big endianness are like the IMB's Z architecture, the Freescale, Coldfire, and OpenRISC. I'm reading these, of course, from a table. I don't know these random by memory. Although, by the way, some of the Linux, I do know that some of the Linux distributions and on Power actually use they did switch to little endian mode, but then some of them might actually still use big endian mode. I think Oracle's Solaris, which is something that just rings a bell, is in big endian. But it turns out that most of the popular ones that we know are using little endian, like or computers, you know, x86, which is pretty much the most popular desktop, and then ARM, because it's by endian, it allows it to go either or. And so you might be asking yourself, which one's better? Neither is better. There's absolutely no difference. Once you actually code this up in the hardware level to work right with the addressing, there is absolutely no difference whatsoever in efficiency or difficulty or extra circuitry and whatnot. I try actually going online and seeing if there's just any possible thing that could actually be better than the other one. And pretty much everybody said that, nope, they are exactly the same, and it's actually some sort of, somebody said it interestingly enough, as a social-political decision. Frankly, I think it was more of a competing thing. Like, okay, you know, it's like Mac when they decide to use some different name for something that, you know, everybody standardized and learned with, and then Microsoft comes up with something else different, and so on. You know, it's just you know, trying to be different. But at the end of the day, for what you should know is, it's important to know if your system that if you're like if you're in the hardware or low level and whatnot. You know, it's important to know which system you're using. And you probably did learn about big endian and little endian in assembly class in 2018. But if you didn't, then, or if you forgot, then this is what it is. So this is important because, you know, if this was being stored, for example, in two bytes long, if it was 2 bytes long, let's go ahead and put that in. So let's say that these addresses could actually hold 2 bytes long each, okay? If that's the case, then with big endian mode, you would be storing 2BC6, like that 6, and then FBC7. Whereas with little endian mode, you would be storing basically backwards, but not fully backwards. But because if these are really 16-bit long now, then you would basically flip the location of these two, but not within the independent bits per se. Okay, because at the end of the day, you know, if let's convert like 2 of these into the equivalent bits per se. You know, the bits of like C7 were actually 0, 1, 1, 1, and then that would be also 0, 1, 1, 1 here. So in both of these, the order is still kept within that section of the bits, right? It's only between the different pieces that you're actually storing it in different locations, and so because of that, actually, you know, technically this would be half a byte. The way that oh no. I see. I have 2 letters. So actually, that's just a 7. So I have to put in the C as well. So let me throw in the C. So 1, 1, 0, 0. There we go. Okay, I was like a little bit confused for a second there. I'm trying to grab this so I can move it. There we go. And then 1, 1, 0, 0. So what I'm trying to say is that, though, you know, within the C and the 7, that order is still kept. You know, we're not, when we're doing little endian, we're not just completely printing everything backwards. We're printing the block backwards or the chunk backwards. But you know, within the chunk or the block, we're not printing backwards, right? So you can see here that the order of the individual bits here that make up that byte are still in the same order there. It's only within the different, you know, blocks, like entire bytes, that it's backwards, okay? So that's the one thing that people typically tend to confuse when they're doing a little endian. They just literally flip everything completely backwards. But no, they don't. And that is why here, when we're looking at the version that is basically a 2-byte width of an address, you know, we're only flipping it like that, and we're not flipping it totally like by putting on the top something of the like C7 FB. No, we're doing FB C7 because that is the order that is here. Okay, so that's the only thing that I want to emphasize with the little endian that people seem to kind of mess up. Okay, so from there, you know, I think the rest of the stuff, I think most of you already understand because of assembly class and because we have talked about it. They mentioned again the instruction cycle, which we will revisit tomorrow when we talk about the pipelining. I guess the only thing that is worth saying is sort of a refresher is what could be the source and result operands that you could get here. And really that boils down to 4 things. They could either go to main or virtual memory. They could go to an IO device. They could go to some sort of register in the processor, or they could be immediate in the sense that the value of the operand is contained in the field in the instruction being executed. So those are the 4 source and results that you know, an operand could have. And then of course there's the 4 main instruction types are, again, you're trying to store data, you're trying to process data, you're trying to move data, or there's some form of control, such as like branching instructions or test instructions, or, you know, those kinds of things. Okay, in addition to that, I suppose the types can be boiled down into these 4 that I have here, and they could be addresses, you know, like memory addresses, like I said, virtuals. They could be numbers, such as floats or numeric representations per se, you know, like integers as a way of representing numbers, but also floating point is a way of representing numbers, right? We also have characters. They could contain some sort of characters. Now, those are numbers as well. In fact, all of these are technically numbers because they're all binary. But what we're saying is that we have a standard, right? We have the ASCII table to represent characters that way. So yes, we consider that its own sort of type. And then logical data, which might be a little bit weird, but that just means that instead of sort of going with a standard like the ASCII table for characters or integer, 2's complement for integers or floating point IEEE 757 or 754, whatever it is, we are saying that we're going to create our own sort of system. And that's kind of what you're actually doing with the IAS, because the IAS that you did, when you were doing your own representation of each bit, so that you could come up with this, when you emulate this up here, this here, basically that's kind of what we mean what we're saying logical data, in the sense that you are doing things on a bit level, or you might be using them as flags and those kinds of things. And by the way, that's actually a more efficient way of storing data in memory, because what happens is that if your memory is in 4-byte increments, and you have something like a car, which it's a lot smaller than that, then it's actually 128 from 0 to 128. So basically, you can keep it in one. The range goes from, technically, I guess it goes from negative 127 to positive 128, I think. But really, you're only using the 0 to 128 range. And of course, you don't really need to have a character of 30, that has 32 bits to keep a count that small, right? To be able to keep a count that small, you really only need 1 byte. And so because of that, technically you're wasting the 3 other bytes, because in memory, some systems could do this, but most of the time, what ends up happening is, if you have your memory as 4 bytes, ideally, if you have 2 cars, then you could split it like this is car 1 and car 2, and then you have like car 3 and car 4. So if you're doing an array, you might be able to take advantage of something like that. But if you have a car and then you have like an integer, what are you going to do? Are you going to stagger the integer to like this half and this half? No, you don't do that. You just sort of waste the remainder space there, and then actually you could keep more than that, because I said a car should be 1 byte, right? I don't think it's 2 bytes. Check for a second. Yeah, 1 byte. Okay. For a second, I was like, is it 2 bytes? But no, yeah, because it's 1 byte. In theory, you could actually keep four. By the way, it was IEEE 754. Just thought about that. But you could keep 4 bytes technically in one address, right? You could do something like that. Character 1, character 2, character 3, and character 4. And maybe if you're doing like an array, you might be able to do that. Like memory might be able to do that. However, if you have a class and it has a car, and then it has an integer, and then it has other stuff, then that one single car is going to take up the 4 bytes, and you're technically going to be wasting them. And so because of that waste, it might be better to manually do things with bit oriented. However, that just makes coding way more complicated, and that's why a lot of people are like, screw that, we'll take that efficiency cut rather than trying to reinvent the wheel at that level to just try to save a couple of bytes. Yes, memory is very valuable and whatnot, but at the same time, so is our time. So, yep, that's pretty much that part. So let's see what else I got in here. I guess yes. They talk about branch instructions, and branch instructions are basically a transfer of control, because you update the program counter based on what the branch is, which could potentially, like, if you got hackish, obviously the system will not let you, as we talked about, like the monitor, we talked about how the OS will not let you do this. But if there was no monitor, you could make you could totally, put a jump statement to jump to a completely different program and like hijack what's happening in the processor. But of course, the monitor would not let you, right? But anyways, the only thing that I wanted to point out from this was actually that they talk about the call stack, which I always talk about in my 202 class, that they will mention eventually. What I basically tell them is that they'll mention it in 326, which they do. But since I saw it on the book in this class, it actually feels more fitting to actually be in this class than 326. So I was like, why not mention it, And so, and I was just talking about this actually yesterday with my 202 class. Yeah, that was actually yesterday when I was showing them recursion. So that kind of the way to understand recursion is to kind of look at the call stack, right? And so the call stack is when you make a procedure, you know, when you start a program in like C++, main is a procedure. So, if you're looking at this from top to bottom, let's go ahead and look at it from like top to bottom. So somewhere in here we have the procedure for main, right? And that is a specific, address in memory, from that address to like address maybe 500 or something. And in here we have lines of code. And somewhere in here we have a procedure call. Let's say that our code is something like foo, and then bar, and then maybe that's it, okay? And so, we have to look at what foo does because that's the first call, right? So this is going to be executing, and it's going to get to this line of code here, and then it's going to stop, right? At that point, we can go ahead and look and see what the code is in foo. And, there's maybe a call to bar in foo. And so what happens here is that when the function call happens here, the procedure call, execution stops here, and so it loads the program counter, I suppose, to whatever in memory the next instruction would be, and then it also loads into main memory here all of the local variables and other things that could be in foo. So if there's like a variable here and function call and whatnot, it's going to load that group of instructions here. Okay, so here's X and here's bar, and so it's going to start going through that, and as it goes through this, it's going to hit bar, and again it's going to pause itself, and then it's going to go ahead and create bar. And let's just say bar just does some code, and then it comes back. So what's going to happen is bar is going to run this code, and eventually this is going to finish, and it's going to come back to where it left off, which is actually we already have an error for that. It's going to come back here and then run the rest of the code down here, and then eventually come back. So as it's coming back though, it's going to get rid of that because it no longer needs it. So it's going to actually delete it, kind of pop it off the stack, and similarly with bar, it's going to pop it off and go back into main, and then continue for the next thing, which is actually another call to bar. Yeah. So then it's going to make another call to bar here, and then it's going to go ahead and run that code, and so on, right? And so, it's tricky because it has to remember where it left off. And so in the book, they have a little chart, which actually I'm going to show. Of kind of how this works, because, the way that I showed it to you is kind of like how memory is allocated for variables. But it turns out that you don't want to just have the entire instructions copied every time you make a function call. You need the local variables of that function call and the parameters because those could be different every single time. However, the actual instructions of the function call, you only really need to keep one copy of that. And so really what you want to do when you actually have a function call is reference the start of the code that you have that one copy of to run that code, and then you want to make sure that you remember the function that called you, which is, like you say, the old frame point, so you can go back to that one. Okay, and so that is how you can have one copy of the function but still have multiple instances of that function, each with their own local variables. Okay, so really you only need to have the pointer to where the code is, and then a pointer to remember how much of an offset you've allocated for memory for the function. Because, like, let's say the function has two variables. Okay, so you allocate two integers. Let's say you're allocating 8 bytes for that function, and maybe another 2 bytes for other stuff. Okay, or 4 bytes. So a total of maybe 12 bytes. You need to remember that you actually allocated 12 bytes, so you know how much to deallocate. Otherwise, if you deallocate 16 bytes or you erase 16 bytes per se, you're going to erase stuff from the previous function call, which is bad. So you need to keep track of that somewhere, and the way you do that is you keep a pointer, essentially, to how much you got to delete. And that way you can overwrite over it. Because really, remember, when you delete things from memory, you're not actually erasing anything. You're simply stating, okay, this is no longer valid information, but it's still there until somebody else overwrites it, it's still just there. And so you will actually be overriding it the next time you go and make another function call. If this is like, you call a function, come back, and then call another function. So just thought I'd mention that since it's actually mentioned in this chapter. Okay, so that's pretty much it for chapter 13. Yep. And now chapter 14 is going to deal with the addressing modes. And that's pretty much all there's to the chapter, actually. That at least what I want to talk about. So I went ahead and wrote down all the addressing modes here. However, the book has a really cool picture for these that makes it easier. So I'm going to go ahead and just switch to that. Okay, so let's go ahead and also magnify this a little bit. So first of all, what do they mean by addressing modes, I suppose? Let's start with that, okay? So remember that, there's address fields in your operands, and they are going to be ideally, referring to some sort of location in main memory, or for some systems, potentially virtual memory, right? And there's different addressing techniques that have been employed to achieve locating where things are in memory. And they all have some sort of trade-off between an address range that you want to have, or addressing flexibility, and basically the number of references that you can basically hold in the operands. Okay? And also, I guess, how complicated it is to calculate the final address. And again, this stuff you will talk about in 370 again, but still, it's good to start bringing it up. So the most sort of easy method for accessing data is not to have an address at all. It's just to have it there. You just have basically the information you want, and that would be basically like A. Be immediate. We're like, who needs addresses when I can just keep the information right in the register, okay? And so, bam, that's kind of just you have the data, and you call it a day, right? The other method is to have an actual address, I suppose, which is a direct address. So here you copy the physical location in memory where the operand is actually kept, okay? So if this is address 500 in memory, that is literally address 500 in memory. There's no magic, there's no switching, no virtuals, nothing. You're literally putting there 500. This is kind of how you're doing, I suppose, your IIS, right? Because you're putting the actual address there. Although this is kind of, the difference is you're emulating, but here it's like it would physically have the address somewhere in hardware will be represented at that location, okay? Then we have C, which is indirect. That's like your pointer system, okay? You basically are holding a pointer, and that you're basically holding the address to a pointer, which then points to the operand, okay? So this is like your typical pointers in C++ and that kind of thing. It's indirect because you're not holding the address to the operand. You're actually holding an address to whoever who knows the address of the operand. Of course, you could go to multiple layers here. If you have like a pointer to a pointer. Some people call it double pointer, but that's technically not right. It's just called pointer to pointer, which is two asterisks, like int asterisk asterisk PTR. Technically, that would be like A goes here, and then this goes somewhere here, and then this goes to another one here, which would be the actual operand, right? So that would be just like adding another level of indirection, but it's still indirect addressing. So again, this is like your regular variables in C++. This is like your pointer variables in C++. Okay? Then we get to register addressing. That just means that's kind of like in assembly when you're doing like add EAX or something, and you're listing the address, the register where the actual data is kept. Then that's basically what register addressing does. You're just referring to the register that actually contains the data. I suppose an immediate example of an instruction would be if you had load 5, and actually it was just 5 here, and that was actually the value. But anyways, so just make sure you don't confuse between immediate and register, because immediate is you're literally holding the actual data in the inside of the operand space, whereas all of these are basically addresses, except these are memory addresses. This is actually a register address, and it might actually be if the register can hold multiple things. then it might be a specific location within the register as well. But typically, I would say it would be just like one register. Another example of that would be like a pointer at the register level, which I'm sure you did in assembly. That's register indirect. So if you're loading something in the register, but that register is not holding the data, it's actually holding the real address of the operand. And the pro of doing this versus versus like C is that the instruction size you're limited to, for example, 32 bits, right? For this, and that has to be split between the opcode and the actual address, right? So this, like your system. So like, your system, you have 1 byte here and 3 bytes here. So you're limited up to 3 bytes for an address, right? But what if you wanted an address bigger than 3 bytes? Well, you're out of luck with this method, or with this method actually as well. This method though, you could keep further away addresses using an indirect method. Because like, for example, I kind of wish that I could draw directly here. I can open up Paint. Yeah. So let me pose to you an issue, okay? The issue is that, of course, you can't keep 32-bit addresses in this system because you need space for the opcode, okay? So at least that would be the situation with direct, okay? But with indirect, what you can do is, for the smaller addresses, you could actually access the data directly. Let's say that this is using the same system as us. So this is 1 byte and this is 3 bytes, right? So for any address that you can fit in the first 3 bytes, which is going to be basically potentially 3/4 of the addresses that you could hold, you can put the address directly and use the direct method. For the remainder of the addresses, what you could do is you could actually use an indirect method and point to somewhere in memory where then you have the real full address that is actually 4 bytes long, okay? And that could be a way to sort of get more space, but you're still limited at that, because what's going to end up happening is that where would you have to store these addresses here that have a pointer? Well, those addresses have to be 3 bytes as well. So then you're not really gaining much because you're giving away addresses. It's kind of like a neutral effect at the end of the day, okay? So that's kind of the problem that you have here. Register indirect kind of resolves that issue, because now what's going to happen is you can load somewhere in the register an address from memory that is potentially 32 bits long, and then using the register indirect be able to access that anywhere in memory. And so that sort of gives you that advantage over using the regular indirect method, that you can have a broader range of addresses up to potentially 32 bits, or technically, I suppose, however big your registers are actually. Because if you have a register that's 64 bits and you have addresses that are 64 bits, you could potentially be okay, but you still need a way to transfer from memory to register, and you would need something here. So again, there's pros and cons, but at least this does allow you doing that. And so that's one of the pros of this method, I suppose. But either way, just so you know, make sure we're on the same page here, that what you're holding here is the location of the register, but you know that this is not actually the data itself. It's a location of the register is actually the address where you have to go in memory. Of course, this is slow because you have to first go to the register, although we all know that's actually really fast memory, and then go to the main memory, right? Finally, we have displacement, which is kind of useful when you're dealing with things like arrays and things like that. And so let's say that you have like an array that starts at a special address, okay? Once you're there, you can hold part of that address here, but then the shift that you need to get to the right member of the array, you could keep somewhere else. You could keep directly here, or in the case like they have here, you put it in a register, and then you basically add both of those pieces of the address together to get to the operand. So we call that displacement. And finally, we have the stack. And there we go. In the sense that you don't deal with any registers, you basically just take whatever's on top of the stack as always going to be what the next operand is going to be. And so An example of this would be those calculators that they call postfix calculators, or prefix calculators, I suppose, could be as well, in the sense that there is no real registers. You're just keeping things in the stack, and you can only ever access things at the top of the stack. And so a postfix calculator would work in this system. So if you did one of those in 202, then you know what I'm talking about, or maybe you did it in 302, or if not, you will definitely do one in 326. And so those are limited because you can only be dealing with one spot at a time, but you can still do anything you want as long as you order things in a very peculiar way in the stack, so you can do that. So like if you want to add two things together, then go ahead and put those two things that you want to add in there so that you can basically take that top of the stack and then call add on the second thing on the stack and then sort the result, as long as you have some sort of accumulator for the temporary spot, I suppose, while adding. So those are going to be your basic addressing modes. And then this is also a little summary of the pros and cons. As you can see, immediate, the advantages that you're not going to memory at all, and the disadvantages that you're limited in how much stuff you can actually store directly there because you're losing some spot to the opcode. Direct is a simple method, but again, you're limited to the address space because there's the size of the opcode that you have to deal with. With the indirect, with the pointer, like I said, whether it's this indirect or this indirect, technically, you both have large address of space, that you can do because you can keep a bigger address in there. But you are going through two memory references, which, it's not just slower, but think of it, the cache. The cache has to kind of, the cache might cache this part, before it loads it in, but it might not cache the second part, and so that could cost a lot, like more misses potentially if you don't have like a smarter cache to do that. With the register example here, the advantage is again that you're not going to memory, but there is a limited space of the registers that you have. If you've done this, if you all did assembly, so you all know about that stuff. Like, if you have like 5 things to compute and you could store them on like EAX and what are the other ones, EBX and ECX and EDX and all those, then that makes it easy because you can just work with those registers. But when you gotta call the load operations from memory and things like that, that's when it gets annoying, right? So if you have registers, if you have more registers, that'd be great. That's what MIPS, that's when they came up with the MIPS stuff. Finally, with displacement, as we said, displacement is where you're kind of mixing together, computing the address by mixing both data in a register and data in the operand here directly. And the advantage of that is the flexibility of the addresses you can do. Like I said, you can do weird, cool things with arrays and whatnot. But it is a complicated system because you gotta make sure you got the right right pieces on each part. So that's kind of the con. And then the stack, like I said, there's no memory or anything. You're always dealing with whatever's at the top of the stack. But again, you can do that for like a postfix calculator, but it only would work if what you're trying to access is at the top of the stack. So if you're dealing with a program that needs like 10 different things at once, it's not going to work with this method. So yeah, those are basically the addressing modes that are discussed in the book for the instruction sets. And then I believe the remaining of the chapter is going to kind of talk about those. And I'm going to give some examples on ARM and x86, which you can just read on your own. But yeah, that's pretty much it. And then finally, for the last thing that I want to talk about is chapter 15, actually. I know I didn't make you read it because I only want to talk about one thing about that chapter. And that one thing that I want to talk about is a little sort of chart or table. It's a table in page 508. This one right here. Because it's pretty cool. It's the key terms of the chapter. And again, this you should know from your previous classes, but I just wanted to go over it very quickly in case you forgot. An assembler is basically a program that you use to take your assembly code and then convert that into actual machine code that runs, which is basically just zeros and ones. Remember, assembly language is basically a bunch of mnemonic codes or symbol representations to to represent a bunch of binary so that you can code things easier. Easier being in quotes, because at the end of the day, it's still assembly. But it's better than coding in zeros and ones, because that would be horrifying to try to remember. I mean, I have a hard time enough trying to remember how the hex to binary table. That's where I put it on the iPad. Now imagine having to remember like a bunch of those for which one is load, which one is store, and whatnot. So yeah, that'd be not fun. Compilers is what basically converts the source code into either the machine language. Although technically, a compiler that goes from source code, like a high-level language, to assembly, you would actually consider that a compiler as well. Do remember there's the difference between compilable languages and interpreted languages. If not, in 326 they'll talk about that. Basically like Java versus C++ kind of thing. Executable code is the machine code itself, ready to run essentially. Instruction set is basically what we've been talking about for the past few days. It's basically all the instructions for that specific computer, and like the actual, what the processor understands, like load, store, add, those kind of things. The other ones down here are, like linker, loader, and object code are related to when you're creating code. So the compiler will give you object code for different files, which you may not need to, but if you have a library, you have to link it to that library. So it goes high-level language code, compiled into potentially object code, link it, and then create executable code, which then you can go ahead and load into main memory with the loader, which is the program routine that's part of the OS, and then you execute the code. So, yep, I just wanted to make sure that you guys remember that from assembly, from 218, because I don't think you really need to know much about this in 370, but it's still, they just felt like something that was useful to actually spend a minute on. But yeah, that's it. From now, the last, we have one more chapter to go over, chapter 16, so I'll do that in a separate video. But hopefully this was short, and if not, well then at least, we only have one chapter left at this point. So thanks for watching, guys, and I hope that you have a wonderful day. Thanks.